Hi, my name's Paul McLellan. I work in corporate marketing here at Cadence. And today this is Semiconductor 101, which is a very basic introduction to semiconductor and in particular to EDA, which is the part of the market that Cadence is involved in. And if you don't know what EDA stands for, then hang around and I'm going to tell you. So we have this intelligent system design strategy. You can see there are various interlocking circles here. Lots of bullet points that might not mean much to you. I'm going to come back to this slide again at the end. Hopefully by then you'll have some context and I can talk about it. Across the top are the end markets, the most important for semiconductor, which are consumer, what we call hyperscale, which means cloud data centers, mobile, that's smartphones, communications, automotive, cars obviously, aerospace and defense, industrial, and health. So I mentioned EDA, and that stands for Electronic Design Automation. If you ask what Cadence does, we're in the EDA industry. We also have another part of the business called IP, which stands for Intellectual Property, which is a bit of a confusing term because it's nothing to do with patents, which is what intellectual property normally means. But in this context, it's little pieces of chips for designers to use. There are two main parts to EDA. Integrated circuit design, which is what we're going to spend most of the time talking about today, and printed circuit board design, because when we've designed chips, they have to go on something. You've probably seen pictures of printed circuit boards. They're usually green, not always. This picture, for some reason, is blue. One of the aspects of EDA is chips are incredibly complicated. If you've probably heard that people like Apple and NVIDIA and AMD, they have chips where they have maybe 50 billion transistors on them. And that means we have to work on very advanced algorithms because we're operating on bigger data sets than almost any branch of engineering. For instance, the recently announced Apple M1 has over 130 billion transistors, the M1 Ultra, and the recent announced NVIDIA Hopper GPU has 80 billion transistors on one die. So those are pretty big numbers when you have to deal with them in any software. And so in particular, they're at hyperscaler cloud scale. So some of the things that we do, something called library characterization, uses literally tens of thousands of processor cores in parallel. And many of our EDA tools use hundreds of processors in parallel, such as design rule checking, for example. So let me start, before I get to more details on EDA, with a little look at semiconductor economics. So you've probably heard of Moore's law, that the number of transistors on a chip will double exponentially every 24 months or 18 months or 30 months or so, something like that. And this has been going on for a long time. To some extent, this picture here is a bit of a joke, but it's showing you how even in the days of vacuum tubes, designs were getting smaller and smaller every few years, starting on the left with lots of tubes and finally on the right with discrete transistors, and that's even before we get to integrated circuits. So if you plot this out, so Gordon Moore actually had 4 data points when he came up with Moore's law, which is kind of incredible. And what's even more incredible is that it's been going on for 50 years, pretty much continuously. One thing to remember, since people aren't in general used to looking at these things, this is an exponential scale. And if you look at it on a real scale, where it's a linear scale, it literally goes flat, 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 and then goes vertical. The exponentials tend to be like that. Seems like nothing's happening, and then everything's happening at once. And we've seen that with talk of disease propagation and things where they also have exponential aspects to them. That in turn translates into the transistor density. We talked about chips that had tens of billions of transistors on them. They're not that big. Over on 10 nanometer, there are 100 million transistors per square millimeter. And on the most advanced processors, that number's kind of doubled since then. But I like to look at what I call the inverse Moore's law, because I think this is what's driven both the semiconductor industry, indirectly EDA, and electronics in general, which is that if you can put twice as much stuff on the same amount of silicon and it doesn't cost much more, then the cost of implementing any functionality in silicon halves every 2 years. So every 2 years it drops in price by a half. That's not so much, but then when you look at 10 years, it drops in price by a factor of 30, and in 20 years, it drops in price by a factor of 1,000. And so in 25 years, something that cost $1 million, like this flight simulator in this picture here, becomes just $200. So a multi-million-dollar flight simulator that I was involved with in the early 80s when I first started in this industry, now it's sold for $250 and called something like PlayStation or Xbox. And the graphics is better and the performance is better. These flight simulators way back when weren't actually very good. And the functionality has improved. On the left, you see all sorts of things: a calculator, a camera, a security ID tag, maps, a GPS device that as a separate thing. And all of those things today are in the device on the right. And you've probably got one of them in your pocket right now, namely a smartphone. But that's not happening. The future isn't what it used to be. Things are slowing down. So processors are sort of the canary in the coal mine. If we look at the improved performance in processors like an Intel x86 or a PC or any of those kinds of things, then they used to sort of improve by 50% a year, and then it slowed to 12% a year, and now we're down to like 3% a year. So we're not getting the same changes as we used to. And so the new normal is a bit like this phone here. On the left was the iPhone when it was introduced. That cost like $349, $350 and went up from there. Now they're $999. So we haven't gone from a $349 to the $30 like we did with the flight simulators. We're not giving away phones at trade shows instead of, as an alternative to coffee mugs and pens, like we did with calculators, for instance. We gave calculators away for a time when everybody didn't have a phone with a calculator on it and didn't really want one. So how do we build chips? So let me first talk a little bit about semiconductor processes, because they kind of have numbers that go with them. They used to be measured in microns, which are millionths of a meter. So when I started, we were at 3 micron, then we went to 0.35 micron, and then when it started to get really small decimals, we switched to writing them in nanometers. So we'd had 28 nanometer, 16 nanometer. Current process or state-of-the-art is 5 nanometers or 3 nanometers. They're just kind of numbers. They used to mean something, but now they don't really mean anything. They're just numbers you can think of them as marketing. 5 is better than 7, 3 is better than 5, but that's about it. And they're made in wafers, so we don't make chips one at a time. We make them on these wafers, and there are 2 sizes. The ones, actually, if you go back far enough in time, there are even more sizes, but they're 200 millimeters or 8 inches, that's on the right, and 300 millimeter or 12 inches on the left. And then we put as many of the actual chips on there as we can fit, where you can sort of see the little sort of square pattern on these chips, and each one of those little squares is a chip. Later they'll be chopped up and put into packages separately. And we build them in fabs, what we call fabs. That's short for fabrication line. And they're factories, really. They're roughly the size of a car plant or something like that. They're huge. Here's the inside of one. The first thing that you notice when I show you this is there are no people there. Basically, fabs are run entirely these days from the outside. The people are controlling them from computers outside of the room. And obviously, occasionally, people have to go in there to maintain equipment and that kind of thing. But in normal operation, everything is done completely automatically. On the top of the picture, you can see those things. Each of those holds 25 wafers, and they move around automatically and move the wafers between machines. And they're expensive. A modern fab costs $10 to $20 billion, and it'll make about 50,000 300 millimeter wafers every month. Wafer starts per month is kind of how you measure how big a fab is. And if you do the numbers and assume that it lasts for 5 years or something, then it depreciates at about $200 a second. And that means you need to be doing about $1,000 a second of business to justify owning a fab, which most people don't. And so we have this fabless revolution. Jerry Sanders, the CEO of AMD, was famous for this statement, "Real men have fabs." It was around the late 90s when there was a famous book called "Real Men Don't Eat Quiche," and this was sort of a play on that. And funny enough, AMD was the first of the companies with a fab to sell their fabs and created a fabless a foundry called Global Foundries. And even more amusingly, they're the first company with a female CEO, so it's like real women don't have fabs. So today there are just 3 leading-edge non-memory manufacturers: Intel, TSMC, and Samsung. In memory, there's SK Hynix, Samsung, and Micron. And in flash, there's a few more: Samsung, Toshiba, Western Digital, Micron, SK Hynix, Intel, which is kind of getting out of that business, but they were in this business. All the other semiconductor companies are what we call fabless. So you may have heard of Qualcomm, who make chips that go in phones, Broadcom, NVIDIA, who makes graphics chips and graphics cards. And they're called fabless, obviously, because they don't have a fab. And the way they actually get their chips manufactured is they go to foundries. So fabless companies, I actually wrote a book on this with Dan Nenny as the semiconductor industry transformed from everybody having fabs to almost nobody having fabs. And the whole way that chips were built got split between the fabless semiconductor company like the Qualcomms and Broadcoms that designed the chips, and the foundries like TSMC or Samsung who manufacture the chips in the fabs that we looked at earlier. So where does Cadence fit in all of this? So we do design, but chip design is not really like other design because it's on a very, very, very short time scale. And I like to look at an equivalent problem, which is to design the Airbus 380, but you only have 12 months. And you're using a manufacturing technology that's never been used before because they've just changed how all the fabs work. And you have to use new software design tools that have never been used before. And then you have to put the first prototype straight into high volume production, ready for the Christmas market. And then start on the next, even bigger plane, since the one you just designed is almost already obsolete and certainly will be by the end of next year. So that takes a lot of investment. So Cadence actually invests about 40% of our revenue, 38, 39% of our revenue in R&D. We have about 6,000 R&D engineers, 1,900 field engineers, and so on, in about 23 sites. It's very global. We've got development sites in Europe, all over the US, all over India, in China, and so forth. So here's a simple flow to show how chips are actually designed. Of course, it's oversimplified. The actual one would have many more boxes. We start there with an idea, and the idea is in your brain, so we have to get it out from there and get it into the design tools. So the way we do that is you write it down in a language called System Verilog. And the first step we have to do is called functional verification. And that's to check that the System Verilog we've written down does what your idea was all about. So if it's a GPU for NVIDIA, that it does the things that GPUs are meant to do. We then take that, and through a process called synthesis, we automatically turn that into a design using little blocks of IP known as standard cells, little blocks of silicon called standard cells. And then we take that netlist and run it through a process called physical design that actually basically builds the entire chip. It doesn't build the chip itself, it builds the design for the whole chip. And then the rest of the process is to check that whole building the whole chip thing worked fine. So there's a thing called sign-off, checks the timing and the power, and then we end up with the layout in a form that we can send it off to the foundry to be manufactured. But before we do that, we run it through a process called physical verification to make sure that what's on the thing we're going to send to the foundry is fine. And then we get to a stage called tape-out. We don't use tapes anymore, of course, but we used to 20, 30 years ago, but it's still called tape-out. So Cadence has products in all of these spaces. So here are the product names. There'll be a short test at the end. So the synthesis tool's called Genus. Our physical design's called Innovus. All of our tools for digital flow pretty much end in US, and all of our tools for verification and simulation end in UM. And then there's another little bit called custom block design, because the bits that we have to design by hand, and we have a tool called Virtuoso and a simulation tool called Spectre for doing that. And we also have PCB. I talked about that right at the very beginning. This is about the only place I'm going to mention it. Our PCB design tools are Allegro, Sigrity, and OrCAD. And then in the IP area, in the sort of bigger blocks of IP, we have Tensilica processors, we have Denali memory interfaces, we have interfaces for almost anything you can think of. You might have heard of PCI Express and other Ethernet, and we have interfaces for those kinds of things. So I said that chip design's not like other design. It's kind of the physics constantly changing. The thing that people care about is also changing. Back in the 80s, we cared about area, because if you could get it built, it would kind of run fast enough most of the time. In the 90s, we got really worried about both timing and area. But we didn't worry about power because the chips were too small. They didn't have enough transistors. It was hard to use too much power. In the 2000s, we started to worry about power a lot as well. And increasingly, we have to worry about absolutely everything all at once. And we saw earlier that they have short, unforgiving design cycles. If you designing smartphones and you miss the Christmas market, Christmas doesn't move. So you kind of miss the market completely. The designs are pretty expensive, $10 to $100 million for a typical chip, maybe $1 billion for a state-of-the-art microprocessor. And of course, you need to have product revenues that are big enough for that. And it's not just semiconductor companies anymore. Companies like Apple and Tesla and Samsung Mobile, they all design their own chips. Google designs their own chips, Amazon designs their own chip, Facebook, Microsoft. Everybody's designing their own chips because they want to control the chips precisely to do exactly what they want. And so that means they've all had to build up design groups to allow themselves to have these special features that they need. So here's one of the biggest chips around, the NVIDIA Hopper GPU, 80 billion transistors. It's designed in around 2 years. But when you design, you multiply those numbers up 2 years, 700 days, 80 billion transistors, it's over 100 million transistors a day. And just to put that in perspective, the largest commercial airliners like a 777 have 3 million parts. And that's counting every single rivet and every single screw and so on. So it's a completely different scale. And the cost of design has been ramping up as design has got more difficult. Over on the left, at 65 nanometer, not so much. And now over on the right, 5 nanometer, much, much bigger. One thing you notice is that pink block in the middle, that's software. More and more of the design of an electronic system is not just the chip, it's designing a huge amount of software that has to run on the chip. Most obviously, there's a lot of software running inside your smartphone, for example. I'm not even thinking of the apps particularly, but the operating system and so forth. And there's another big difference. Planes have to fly eventually, but nobody actually does what I jokingly said earlier, which is to put the plane together, put it on the runway, and see whether it will fly. But chips are expected to work first time. There's a lot of cost involved if they don't, and in many cases, it takes 5 or 6 months to make changes and then to get a new chip manufactured in the fab. So a lot of the tool investment is in risk management because, like, the plane has to fly. And a design is expensive to tape out. The masks cost literally millions of dollars these days to build, which is the thing that gets built from the design after tape out. And that's what actually is used in the fab as part of the manufacture. And the cycle time to get a wafer through the fab from beginning to end is literally months. 5 months is not unusual. So people do a huge amount of verification before they tape out because they're going to have to wait several months to find out whether that chip works and it had better work. And you might think that, well, you can just sort of make everything a bit pessimistic, but that doesn't really work because Fabs are so expensive that if you are pessimistic, you may as well have used the fab from the generation before, and because you're not taking advantage of the fab that you've just built for $10–15 billion. So let's move on to systems. So chips go on boards, and in this case they're green like they were meant to be. And increasingly, we put more than one chip inside a package, which we call system in package. The catchy name for that is more than more, because it's another way of building big systems other than Moore's law, which we talked about earlier. Surprisingly, we actually put holes that go all the way through the chip and come out the back, known as through silicon vias, and that's how we can stack several chips on top of each other and connect them all up without having to do something weird and wire them up manually. Systems contain software. I mentioned that. Those were the pink blocks on that big bar diagram. And they contain a lot of software. There's 25 million lines of code on an F-35 jet fighter. There's 100 million lines of code in an ADAS-equipped car with things like automatic emergency braking and recognizing traffic signs and so on. And our simulators are just too slow to bring up the system to even boot the operating system. So when you turn your phone on, the time between when you first press the button and the phone's kind of ready to use, and then that's the operating system booting. And that's literally billions of instructions being run. So in order to do that, we use hardware like we see here. There are two kinds of hardware. One's called emulation, which is very fast, and allows you to debug the hardware really easy. And the other is called FPGA prototyping, and that's even faster, but it's not very good for hardware debugging it, but it's much more suitable for the software people because it's so fast. So our emulation system's called Palladium, prototyping one's called Protium. So we use emulation to get the chip right, and then FPGA prototyping to get the software development done. And you don't tape out the chip until you know that the software will run. And so that's what these hardware boxes are used for. So I said we're in the EDA software business at the beginning, but we're also in the EDA hardware business if you look at these boxes too. So who uses all these chips? What's driving the semiconductor industry? And it drives the electronics industry directly, then that drives the semiconductor industry less directly, and that drives the EDA industry even less directly. And so we're the tail that gets wagged on the end of the dog. So the semiconductor world changed kind of dramatically on the morning of January the 9th, 2007. A Starbucks barista took a strange phone call from somebody, and it asked for 2,000 lattes to go. And it turned out it was the first non-test call on an iPhone. Steve Jobs on the Yerba Buena Center announcing the iPhone called up the local Starbucks and ordered 2,000 lattes to go before he canceled the order. And mobile is the biggest semiconductor market. There are about 1.5 billion smartphones shipped every year. It's flattened off. These are the numbers you can see, the green bars. And so it built up from small numbers and then grew steeply. And now we're close to a replacement market. Most people buying a smartphone already have a smartphone and are selling the one that they've got or scrapping the one that they've got. So it's not like we're in that high growth phase anymore. Okay, the next biggest market is automotive. And it's actually two markets. Historically, automotive has used old semiconductor processes that are at least 10 years old, low complexity, very simple, and the focus has been totally on reliability and cost. But that doesn't work in the modern world of automotive. We've got advanced driver assistance systems like automatic emergency braking. We've got autonomous vehicles, or we're getting close to having autonomous vehicles, and these require advanced processes, but they require automotive reliability as well. And so it's been a challenge for the last few years to bring these two things together. The people who know about designing in advanced processes don't know much about reliability. The people who know all the automotive reliability stuff don't know how to build these big designs. But there are a lot of them. There are about 100 million vehicles a year designed. You can see the ramp over on the right. And that's actually not the number of vehicles, that's the percentage of the cost of a car that is actually in the electronics, and it's forecast to be 50% by 2030. Aerospace, in the early days of semiconductor, aerospace drove everything. The Defense Department would buy all the chips and put them in planes and so forth, and actually missile defense systems more than planes at that stage, I think. However, the production volumes are pretty small. A program manager who used to work for a mobile semiconductor company said he's never seen a production order that's more than the chips they would give away for free in the commercial world. But their big challenge to some extent is security and the lifetime of their chips, of their systems. Right? The B-52 bomber is, I don't know how old now, was it 60, 70 years or something like that. High-performance computing, so cloud data centers. Obviously, the big people in that are Amazon Web Services, Microsoft Azure, Google, and then there's a bunch of them, Alibaba and Co. in China. So that's servers, routers, storage. Increasingly, it's optical. The networks are optical rather than copper. And increasingly, another thing that's driving it is training of deep neural networks for artificial intelligence. Then the Internet of Things. There are lots of things. Because they have their own market, cars and mobile phones are not really counted as things. So we're talking about things like Ring doorbells and garbage cans in cities that tell the city when they're full and that kind of thing. The big challenge here is it's a very, very fragmented market, and it's unclear how you make money on these very cheap chips. Some of the stuff that's going on in the cloud seems to be moving to the edge. Things like these home voice-activated appliances. Increasingly, people want them to do some of the inference in their living room rather than uploading everything or having the feeling that everything that they're saying in their living room is being uploaded to the cloud and listened to by whoever. It's very, very fragmented, as you'll see here. You're not meant to be able to read this, of course. All you're really meant to see is that's a subset of all of the companies that are in the IoT business. And many of them are not designing their own chips. Many of them are just designing their own system and using standard chips in order to do that because they just don't have the volume. We looked earlier at how much it costs to design a chip. Well, if your chip's going to cost $50 million to design, and then you need to be selling a lot of them to justify that investment. And it's a lot easier to spread that investment over the large number of these IoT companies. Memory is another part of the semiconductor market. I'm not going to talk very much about that. It's never or rarely designed as part of a project. People purchase it from specialized memory companies. I mentioned the names of these ones earlier. It's a big part of the market, 25% of the total semiconductor market. Of course, people use design tools like Cadence's custom design tools to design these memories, but they do very, very, very few designs, right? They do a design, and it's all about massive scale of manufacturing. So let's get back to the intelligent system design slide I showed you at the beginning. So in the center of the three circles on the left is really where I'm going to focus. Design excellence is really what we've talked about mostly today, which is how do we design chips and how do we ensure that they work first time, and how do we make it so that the designers who use Cadence tools are efficient. The next level out, system innovation, is where the PCBs and those systems in packages and things showed up. There's a lot of analysis that goes with that. You can't just randomly chuck a few chips into a package and expect it to work without checking that it works, so there are tools for doing that. And then outside, there's pervasive intelligence. Increasingly, there's artificial intelligence built into the tools that Cadence supplies. And of course, it's driving all sorts of the electronics industry at the customer level. So let's talk a little bit about Breakfast Bytes, which is the blog I write. It comes out daily on the Cadence website. It's not all about Cadence. Of course, when we announce a new product, I write about that. But I write about the entire industry, the semiconductor industry, the end market, some of the manufacturing stuff too. The easiest way to find it is www.breakfastbytes.com, which will take you to a much more complicated address on the Cadence website. Or better still, subscribe to Sunday Brunch. At the end of any Breakfast Bytes post, you'll see a thing saying sign me up. You'll get one email on a Monday morning with the post from the week before, so you can see whether any of them interest you, and if they do, you can just click on it and be there in one click. So that's Semiconductor 101.